In the third part of the compression unit, I want to talk about text transforms. These are things that don't by themselves compress text, but they help other compression methods. And one of them in particular is at the core of the modern achievements in compression and compressed data structures and text indexing. So it's definitely a very nice idea to hear about. So the idea of text transformations is to help compression methods overcome limitations. What we've seen so far is that certain methods can exploit certain types of redundancies. For run length encoding, these are long repeated runs of the same character. For Huffman, it's some characters that are very frequently used and others infrequently. And for Lempel-Ziff-Welch, if we have many repeated substrings not too far spread apart because of the dictionary size, then Lempel-Ziff-Welch does well. Unfortunately, methods can be very stupid whenever it goes a little bit beyond that. For example, Lempel-Ziff-Welch doesn't pick up any repetition if they're too distant. If the dictionary is already flushed, then we will not profit from these. And this is inherent. You can make the dictionary big, but then your code words are longer and you waste space on that side of things, unless you do extra steps after it. Or you make your dictionary small and then you miss out on this long distance repetitions. Huffman encoding totally ignores that the frequencies can be different in different parts of the text. That's particularly relevant for biological sequences. It just looks at the global average. How often does each character occur in the entire text? And so if you have local clusters where some characters are more likely than others, Huffman is totally blind to this. And run length encoding is very, very picky in that it only allows exact repetitions of the very same characters, and any slight disturbance completely throws it off. In particular, if you have a long repetition but it's alternating of two characters, run length encoding would completely fail and not achieve any compression. So text transformations have been invented to at least shrink these blind spots of the known compression methods. As I said, they don't themselves reduce the space usage at all. They might even make it bigger in some cases, but they make the existing redundancy, they transform existing redundancy in the text into a slightly different form. And that's often one that can be picked up by existing methods. And we'll see two examples of these. The first example is the move to front transformation. You might have seen move to front in a data structures class for self-adapting linear lists. If you haven't, it doesn't matter. That's where historically the idea came from, I think, but it doesn't really rely. What we will do doesn't rely on that use. So what is move to front? Suppose you have a linked list of items and you repeatedly access items in that list. Then the linked list is not sorted, but you would like to profit from something like the same element is always accessed, or some elements are much more frequently accessed than other elements. And you don't know this information up front. So a simple heuristic, a simple idea for exploiting this is that whenever an element is accessed in this list, whenever you needed it, you move it to the front of the list. So a linked list, right, is just like this. And let's suppose here is your element x, and you access x now. So what you would take is, what you would do is you take the entire list and leave everything unchanged except that you now take x out, move that to the front of the list, And because it's all pointered, you can do this without moving the other elements. And you shortcut the old pointer for x. So with changing 2 pointers, you can do this. The actual cost for the access is bigger than because you have to start from the beginning and walk along the list until you found x. But the cost of changing the list is really just 2 pointers. And there's some theory about this move to front heuristic that I won't get into here, but it's a cute topic in data structures that this heuristic is enough to learn the access probabilities of objects in an effective way in a specific sense. But let's leave it vague at this point. We will use here the same idea, but we abuse it for something very different. We will use a move to front list for the alphabet characters. And when we encode a character, we find it in the list, and we use as the code for this character the index in the list. How many positions did I have to walk back in the list? And we use its old position because after it was accessed, it always becomes the front of the list. But we can always store 0, then we can't decode. We cannot invert this transformation. But we can store the old position in the list and then do the update. So that means our code words now are integers from the same range as the alphabet is big. That's different from many of the other methods we've had. It's not a binary alphabet, but a much bigger one. Maybe if you think about this, maybe we'll do an example first. Okay, this is what it leads to. Let's see an example first. And to get started, I want you to practice the move to front rule itself. So you have a move to front list, as I just described it, where whenever you access something, you put it to the front. And so this is the current content. And now you access A. What is the list content after this single access? So this is just I abused the word cloud poll, but you can just type in the content of the queue of this move to front list. And I would say put spaces in between the characters. Okay. Some answers are dropping in, and that seems fine to me. Maybe I'll give you a little bit more time, so we have a few more answers, and then I'll show the results. So remember, move to front works as follows. You access the element in the list, and then you take it out and put it in, well, you take it out and put it in front of the list. Let's see, at least 10. Okay. So we have a wild collection of ideas and also of different spellings. That makes it a little challenging. But the fat one that was sent a couple of times is the correct one. It used to be XYZ ABC. Now we access A, so that means the A is moved to the front, but the rest stays the same. So we have A, X, Y, Z, and then BC is left as it was. Okay, so that's how a move to front works. You, as I've had it in this tiny example here, this used to be X, Y, Z, and now I used X here again. I used X here instead of A, but it was A, B, C, and then after that you would have A, X, Y, Z, B, C. Another box for the C. Doesn't fit on the slide. That's how it works. Now, first question is, why should that be any good? Second question is, can we invert it? Can we get the original text back? The answer is yes in both cases. Let's first look at the second question. Okay, it doesn't work so well. I want to show the two pseudocodes just next to each other because they do the very same thing. And it's nice to see how they work in sync, because that makes it explicit how you can invert the move to front transform. So for encoding, we start with a list of all the characters in the not sure if this should be CS instead, because it's the source text. Well, we only have one alphabet, and the output alphabet is the numbers anyways. So we take a list containing the alphabet elements in sorted order. So this is important because we have to know how to start. Then for encoding, well, initially there's nothing encoded, so we start with the empty string for the coded text. Then we walk through the characters in the source text. That's the next character. We find the position of C in this list, so we walk through the list and check if that is the character we find. And then we store that position as the next code word. And finally, we move C to the front of the list, and we repeat. We do the same thing in the decoding. I have to fix this here. So decoding starts building the same list, the alphabet in sorted order. Initially, the decoded text is empty. We walk through all the coded symbols, which are the numbers, and then we find the pth position in the list and return that. Okay. And then again, we do the same move to front. So you see how these are synced up. They start with the same list, and they always change the same list. They change the list in the same way, and they extract the characters in the same way. So by putting the code next to each other like this, it becomes obvious that they do the very same thing. So encoding goes from characters to numbers, decoding goes from numbers to characters, but they always make sure that these two things remain in sync by keeping the move to front list in sync. I have a small example for you on this, but I want to go through this fairly quickly because I think it's fairly easy. Here's the alphabet sorted initially in the list. Now, you start with I, you find it in the list. It has position 8, so the first output character is 8. And now you have to move I to the front of the list. So you see how these all jump one position to the right, and I jumps to the beginning, right? I jumps to the beginning, then comes A, B, C, D, E, and so on, up to H. The next character we want to encode is N. It's found at position 13, so we output 13 as the next code word. And again, move N to the front, and everything between the front and N, one position to the right. So one more time, loop, there it moves over. The next character is E, so we find it at position 6, store the 6, then move E to the front. Gives you this list, and so on and so forth. I think the concept is probably clear. So you can go through this in detail if you feel like it, and well, double check if you arrive at the same result. Now, an interesting observation is what happens in this transformation with certain features in the input text. For example, when the input source text has a run of same characters, like here, what does that correspond to in the coded text? And what does the run in the coded text mean for the source text? That's two interesting questions to think about. I think I should put these on top of each other so that this becomes more visible, but the first question is really a run of characters in the source text means after the first character from the run, we have that character at position 0. So all remaining characters from the run will have a 0, will be represented by zeros. So we find zeros in the coded text whenever there were repeated characters. And what does a run of a certain digit in the coded text mean? For example, here, the 3s. Those are these 3 characters. They're not the same. So what does that mean? Well, it means that, maybe let me do this in a different color. Different color. Run in C. It maps to these 3 characters. And you find 3 positions back, the same substring occurs. So runs in the coded text mean there was a repetition in the source text. And that's a pretty neat result because we know how to exploit runs in the coded text with run length encoding. And we didn't know, well, at least not with run length encoding, how to handle repetitions of this kind. Lempels Welch would have been able to pick this up if it's short distance. But that gives you a first idea why move to front might be useful. As I mentioned before, move to front doesn't really compress. That's why it's called a text transformation. It doesn't really make the text itself shorter, but it allows for other methods to work better. It's basically used as part of a longer pipeline. In isolation, it doesn't really do a lot of good. The code words that come out of the move to front transform itself have to be represented in binary somehow. You could use the Elias gamma code that we used in run length encoding. And that makes sense because smaller numbers get shorter code words in that code. If we have local clusters of characters, that will lead to small numbers after the move to front transformation. So that can work well. And the other option is, of course, a Huffman code. Then you would have to do the 2 passes, but it achieves better compression. But the most striking reason why we want the move to front transformation is actually only clear after we talked about the next transformation, because those 2 in combination are the really effective compression methods.